Hello, welcome to another Stat 510 video. In this video, we're going to talk about random variables. Okay, so to start talking about random variables, we have to jump right into the most confusing part, which is what is a random variable? The name is not particularly helpful because in a lot of ways, a random variable is neither random nor a variable. That's not entirely true, but we need to be careful. So what a random variable is, it's actually a function or a mapping. And what it does, a random variable, uh, often we name a random variable something like x or y or z. We generally use capital letters. This random variable x, we're saying it's a function that maps from the sample space, that is potential outcomes of a random experiment, to the real numbers. So yeah, it is a variable that takes potential values, but the way it does that is it's actually the thing that maps from the sample space to the numbers. So it's a function, and it is random, but the mapping is not. The mapping is deterministic. Like if given an outcome in the sample space, there's a it gives you a particular number output. The randomness is that the random experiment randomly generates an outcome in the sample space. Therefore, the output of the random variable is a random number. But it's the random variable in and of itself is a mapping. So you have to be a little bit careful there. But often we sort of lump all of that idea together, and we'll talk about the distributions of the random variables. That is, how often do various numbers pop up when that random variable is applied to a certain sample space or the outcomes of a particular experiment. Okay, so a quick example here. Make myself just a little bit smaller. We'll adjust that as we go. Okay, so let's say we flip a coin twice or flip two coins. Either way, it doesn't really matter. Okay, so I'm going to define a new random variable, call it x, and it'll be the number of heads observed. Okay, so first we note all of the possible outcomes of this experiment, and that is the sample space. And then I'm going to apply this function to each of those outcomes, which the function essentially looks at the outcomes and counts how many heads there are. So I think I can do this. So there's 2 here, 1 here, 1 here. There's none here. Okay, so now I want to look at this no longer with the sample space attached to it, but just as a random variable now. So the possible values of the random variable are 0, 1, and 2. And so now I want to calculate the probability of these potential outcomes. So the probability that x is 0 is 0.25 because that's the probability of seeing tails and then tails again. Same thing here to see heads and then heads again to get the random variable value of 2. That would be 0.25. So by process of elimination, this is 0.50. Now, a note on the notation here. So first of all, this probability statement is about, this is a random variable, and this little x is a placeholder for a possible value of the random variable. So what did I just say? Placeholder for possible value. But even that notation, it's kind of a shorthand that doesn't necessarily make sense. What this notation really means is the probability that we observe an outcome in the sample space such that the random variable applied to those outcomes outputs the value that we're talking about. That's just obnoxious to talk about all the time. So this probability that big X equals little x is sort of the notation that we use that means that all the time. But keep in mind that this is what that actually means. Okay, so Right, so now we want to talk about related concepts. So first we want to define the cumulative distribution function, otherwise known as the CDF. Cumulative because it basically accumulates probabilities up to a certain number. So this is also a function, and I want to note again that so this x here is big, this x here is small. So the big X is the random variable. So that the subscript big X is just to note that this is the cumulative distribution function for that random variable. Sometimes we won't put that subscript when it's obvious from context, but sometimes we will when it's less obvious. And then the small x here is the input to that function, and it's in a lot of it could be a potential value of the random variable. But anyway, so the CDF is a function. It inputs a number, but then it outputs a number, but that number is a probability. Therefore, it is between 0 and 1. So the actual definition is that it's the probability that the random variable takes a value up to or equal to that little x that we input into the function. There's something to be said here about, we statisticians are maybe not the best at notation. Why couldn't we have just put some arbitrary letter here, like a K or something? You can make this a K. It would be less confusing, but I don't make the rules. And we just all learn to sort of deal with this, I guess. But the big X, little x, I'll mention it a few more times, so there's something to keep in mind. Okay, so back to that example that we were looking at. I want to draw this CDF now. So let's see. So at x is 0, there's a 25% chance. And then so something like this. And then at x is 1, we get a big jump. So we're going to get a nice step function here, something like this. And then like that there. And then this extends that way. Okay. So let's think about some things here. So some quick calculations. So like something like the CDF of, I don't know, 0.5 would be right about here. So 0.25. The CDF of, let's say, how about -1? So that's somewhere over here. So let's say right there. So that's 0. Then maybe something like, how about at exactly 1? So that's here. So that's this point here. So that's 0.75. Then we'll just say, what's something like f of 42? Well, that's way out here somewhere. So that's clearly 1. I just realized that as I was writing that, my face was overlapping it. Okay, we might move me around just to keep me on screen. Okay, cool. So you might notice some things. So we sort of see that the CDF only goes, well, I don't want to say that. It never goes down. It only goes up. So it's non-decreasing. We see it's kind of got that step function thing. I mean, it won't always be only steps, but there's some commonalities here among all CDFs. Oh, actually, one more thing before that. So why are we interested in CDF? So because it tells us, it's sort of a compact way of saying everything about the distribution. So we want to talk about this theorem that talks about equality in distribution. So let's say we have 2 random variables. So x with a CDF of f. So this is the CDF of x. And we also have g, and this is, y. Y is the random variable, and then this g is the CDF of y. I don't like that tilde. That's better. Okay. So if f of x, the CDF of x, equals g of x, the CDF of y, for all values x, then the probabilities are the same for all potential subsets A. So let's think about this though. But so in other words, if two things have the same CDF, they have the same distribution, and you'll get all the same resultant probability calculations with those two distributions. But that does not mean in this case that x is equal to y. It only means that their distributions are the same. And one of the classic examples to counter this is a really simple random variable x that takes two values, 1 and -1, each with probability 0.5. And then we define y to be the negative of x. Oh, I should also say that when this is true, we write that x is equal in distribution to y. Okay, so in this case, with what we have laid out here, y is equal in distribution to x. That shouldn't be too hard to see. But if we observe x and it's 1, that necessarily means then y has to be equal to -1. And then if y is 1, well then x is -1. So necessarily, they never take the same value at the same time, but the distribution, so like the probability that x is equal to 1 is equal to the probability that y is equal to 1. Something to keep in mind. Okay, so now back to what I was saying about this graph here should have hopefully prompted you to think about some of the overall properties of the CDF, which I kind of assume you've seen before, but these three properties. So if a function goes from the real numbers to the set 0 to 1, that function is a CDF if three things are true. So 1, it has this first one here, it has to be non-decreasing. Okay. So that's what I was saying before. With the CDF never goes down. So as x goes up, f of x either stays the same or goes up. Okay, what's next? This property we call normalized. And in a lot of ways, together with the non-decreasing property, what this is saying is that if you basically, if we look at this graph, if you go to the left, eventually you're going to get to 0, and if you go to the right, eventually you're going to get to 1 because we're outputting probabilities. Okay, and then lastly, this last one we would say this is notation for it is right continuous. Okay. So those are three things you need to have a CDF. Oops. Okay. All right. So now we want to talk about two broad categories of random variables. The first are discrete random variables, and these are random variables that can take possible values. Take a countable number of possible values. So that could be a finite number of values like we saw in this example, 0, 1, and 2, or it could be something that's countably infinite, say like the natural numbers, 1, 2, 3, 4, 5, 6, counting numbers like that, up to infinity. Okay. So when you have a discrete random variable, it has this thing called the probability mass function, which we call the PMF. And it is literally just the probability, which I've been doing like this, the probability that x is equal to some value. So the probability mass function, you input a possible value, it gives you the probability. It's almost trivial to write this down, but we need to do this to contrast it with continuous distributions, which we have here. So we say x is a continuous random variable if there's some f such that these conditions are satisfied. Move me. So 1, that function is 0 or above. If we take an integral for all possible values of that function, we get one. And this last condition here about how to get probabilities, if those things are met, we call this the PDF, the probability density function. And so the big difference between a mass function and a density function is that mass functions give you probabilities, density functions do not. They need to be integrated like so to give you probabilities. Right. And so I'm blanking kind of on why I had the slide. So this tells us the relationship between the PDF and the CDF for continuous random variables. Yeah, and then we can also get the PDF back by differentiating the CDF. Okay, I think I should have had this slide come next. So I wanted to point out just a couple things that sometimes are surprising to folks about a continuous random variable. One is that the probability that it takes a particular variable is exactly 0, and then 2, densities can be above 1. So for example, here we have a very simple probability density function. It takes the value 2 anywhere between 0 and 0.5, and then otherwise it's 0. I would note that sometimes the 0 otherwise, we may suppress that when we're talking about PDFs, but it's always lurking there, more or less. But so I think it should be clear without even doing the algebra or calculus algebra, it's really just algebra here, that this will integrate to 1. We see a rectangle here with height 2, width half, and 2 times half is 1, I think. So that works out. So this is valid. And so right away, note that something like f of 0.25, which is like here, is 2. So that shows us this. And then the other thing I wanted to note is, so let's say the probability that x equals 0.25. Well, now since this is a PDF, we have to do this to calculate the integral. So this is going to be the integral from 0.25 to 0.25 of 2 dx, and then I'm pretty sure I can do this at 0. And so that's why we get things like that. Okay. Some additional properties of the CDF here. Right. So, some notation I should probably mention. We have this is going to be like this. Y. Okay. So, so this is sort of noting that if we go back here, the phraseology right continuous left limit sort of comes into play. But for example, if we wanted to calculate the probability that x equals 1 here, that would be basically the gap from here to here, which is 0.5, which we see here. But this, where is that? That notation is how to do that, basically. This here, I'm going to note, relates to this here. This is written incorrectly. This should say that, otherwise it wouldn't work out. Wait, no, that's not right either. Hold on. Right? Because no, that's not right either. Why? I'm gonna check just because I don't want to be wrong and then I have to go back and fix this, but I'm reasonably certain that I have it right now. I'm embarrassed that I'm checking this, but because I wrote it wrong, I have to, yeah. Okay, there we go. That makes sense. But basically, if we had some sort of, let's say, arbitrary PDF. I don't know if that's a valid PDF. Something like that. So if we wanted, so here's some value x. So the CDF there would be this, and this is that probability here that we're interested in. That's basically the complement rule, but with a CDF. I don't know why I just spent so much time explaining that. I'm sure everyone understood that already. But I wrote it wrong, so I had to fix it. Okay, and then this fourth point here is noting that. So this is sort of all a consequence. Again, this is because the probability that x equals some particular value is 0 when you have a continuous distribution, and that's why these things all hold. But basically what I want to say is note that the fourth bullet point only applies to continuous random variables, but I want you to maybe think about why this one works for both continuous and discrete. Okay. What is next? Okay. So now I want to talk about this notion of named distributions. So we can write down any, valid PMF or PDF and then like calculate things based on it, right? But I think what you'll find is that a lot of times we're going to work with distributions that you've seen before and that are really common. So a lot of times a textbook in probability and statistics will have a table that, well, here, let's make myself a little bit bigger here. A table that looks maybe something like that. Let's pull a few other random books. Let's see, I think Hogg and Tanis has it right in the front cover, like this. I'm very bad with mirrors. I'm sure Casella Berger has one too. Yeah. This one's a little less densely packed, but the point is, I want to make myself small again. The point is, for a lot of distributions, you can just look up things about them, and there's a lot of things that are known about those distributions. And I think I said in the welcome video to the week, if you're following along in the class, I mentioned Wikipedia here. So if you take any of these names of distributions I have here, again, you can look them up in tables on books, but also if you plug any of these into Wikipedia, it gives you a really nice summary of a lot of things about the distribution. It tells you the parameters, the potential values. It tells you the mean, median, mode, variance, moment generating function. I'm blanking on what else it has. It'll often tell you how to. We're not here in the class yet. It'll show you estimators of the parameters via MLE and method moments. Basically, it's my opinion that in a first probability class, you probably saw derivations of a lot of these things, and we're told a story about like, here's what it's used to model, et cetera, et cetera. Now we're just going to assume all that's known, but I don't expect you to have all these things memorized. So, reference tables, referencing Wikipedia, these things are all fine for all these random variables here. But so I want to mention a little bit about notation. So we say X has distribution F. And so with that notation, that would generally imply like F is a CDF. But the other way we use this notation is in the following. So we say, like, for example, here, this says that X has a normal distribution with parameters mu and sigma squared. Okay, so note that here, normal, I want to say, it defines what I call a form of a distribution. So that is, so normal is a bell-shaped thing, but where the bell is defined by the mean. How fat or skinny the bell is defined by the variance. So I like to say that the parameters define the very specific distribution. Um, like that. Okay, so all these distributions I have listed here, unless we specifically ask you to, you'll never need to say calculate the variance or derive the variance of one of these things. Just look it up in a table. Obviously, we haven't even introduced mean and variance yet, but I'll say this a number of times. Okay, but so I don't know if I want to call this an example, but sort of let's look at this idea here a little bit. So when I use this phraseology here, like x has a binomial distribution with parameters n and p, what that tells me is everything we see written here. So that tells us, hey, here is the PMF. Here is, I'm going to call this the sample space, even though it's not sample space. Oh gosh, can't write. That is these when you apply the random variable to the sample space, these are the potential values for the random variable, and then I'll call this the parameter space here, and to a certain extent here, although in this case the parameter space defines a little bit about the sample space, like the number of coins you're going to flip or whatever. But so for this to be a valid PMF, P has to be between 0 and 1, and that's where the parameter space comes from. Okay, but like I said, this is really only defining the form of the distribution. If I specify particular values of the parameter, so if I say with n is 20 and p is 0.3, well, then we get the specific PMF like this, something like this. What is it? 0.3 to the x, 0.7 to the 20 minus x. And this is valid for x 0, 1, 2 through 20. Okay. And again, I'll just make a case for Wikipedia. We'll have a bunch of other things that you get for free when you know that this is what you're working with. Then just to rehash this idea, so here's another example. So like I said, when you have a normal distribution with parameters mu and sigma squared, that's telling you that compact notation tells you the rest of this. It tells you this sort of arduous PDF here, and then the possible values the random variable can take, and the possible values the parameters can be to keep this a valid distribution. Okay, so yeah, again, hopefully you've worked with many of these distributions before, but if you haven't, simply head to the Wikipedia page to tell you everything you need to know about it, and we expect you to be able to use all of these and use them also with R. Hopefully you've done all of these things before, actually, but just a quick refresher that for most of I think every distribution I listed there, there is a D, P, Q, and R function associated with it in R. So for example, like on this slide that I have here, star would be replaced with the name of the distribution. So like binom for binomial, norm for normal, geom for geometric. On the course website, I listed a reference document with all this information. So you can look there for a list of the things to insert into star. But I want to talk just high level. What do the functions do given a distribution? So pick your favorite distribution. Imagine that's what we're talking about when we say star here. Okay, so D star, that gives you either the density for a continuous distribution or the mass function for a particular distribution. So you input a value, it outputs the density at that value. And so the star, that's where you put the distribution name. So that'll tell you the form of the distribution. But then as arguments of the function, you also need to supply the parameters to give the specific distribution that you want a calculation for. But before I even go further, a warning there, right? A strong warning. The parameters that R uses are not necessarily the parameters in, say, one of these tables. So what I mean by this is twofold. One is that the names that R uses for them are probably going to be different than the Greek letters that we often use when we write them down mathematically. So first you need to understand the relationship between the Greek letters and the PMF that we're talking about, and then the name that R uses for that. But then sometimes different, say for example, an exponential distribution, you can write it in two different parameterizations where you either use like a rate parameter or a mean parameter. And so R will sometimes have the ability to do both of those, or sometimes it'll only use one. You need to make sure you're using the same thing. Something like a geometric distribution, some people started at 0, some people started at 1. So my warning here, what you need to do is read the docs. So you need to pull up, say something like question mark D norm or question mark DEXP for exponential. So when you pull up the documentation of one of these functions, it'll show you D, P, Q, and R all simultaneously. But it'll show you the PDF that it's actually using, and it'll tell you how the names of the R parameters match back to the Greek letters. So I'm not going to go through doing that because it's different for everyone, and I don't want you to memorize it. What I want you to know is that you always need to read the documentation of the function that you're using. That's a stronger lesson than just memorizing whatever thing I go through. Okay, so moving on though. So D gives you the density or a mass. So P stands for probability, and what the CDF gives probabilities, so that's why they use P. So yes, technically PMF and PDF start with P, and that's confusing, but only the PMF gives probabilities and the density doesn't give probabilities, so that's why you use D there. That's why we use P for CDF, because it always gives us probabilities. So P norm, PEXP, those are the cumulative distribution functions for those distributions. Okay, so Q is the opposite of P. So it gives you the quantile. So it's the inverse CDF, basically. So this CDF undoes the quantile function and vice versa. Then last is the R. So what that does is it will generate random observations from the distribution that you've specified. Right. So that's just a brief recap. Hopefully you've seen all of that before, but I can't stress this enough that sometimes you need to read the documentation, especially with respect to parameterization of the distributions. Okay. Lastly, just a quick note about transformations of random variables. Sorry. Okay, so something that will often happen is we'll have some random variable x, and then we define a new random variable that is some function of x. So we could say y is a new random variable that is x squared, or z is a new random variable that's x minus mu over sigma, or y is a new random variable that's e to the x, or generically, y is some function of x. And we say, well, what's the distribution of these new random variables? So basically, I could do an hour-long video on how to tackle these, but I'm just going to say you've seen these before, and we're going to do a couple examples on homeworks, but it's not a focus of this class. But so you could use the distribution function technique, you could use the change of variables technique, you could use the momentary function technique, although we haven't talked about momentary functions yet. And all of those, I should say, And sometimes there's known relationships between random variables. So honestly, like if I told you that x here was normal, you should be able to immediately tell me here that z is standard normal. If I told you that x here was normal, you should tell me that y is log normal, and you should be able to look those things up. But you should also be able to use the techniques to derive the distribution of an arbitrary random variable that was defined to be a function of another random variable. Okay, but we'll look at practicing those on homeworks, and if you have trouble with them, please come to us on office hours, and we'll sort of walk you through whatever technique you're trying to apply there. Okay, yeah, so that's all I have to say about single random variables. So as always, if you made it to the end of the video, good job, and I'll see you in the next one.